Alright, 8.4, we're going to extend some of the work that we've done now to having the universe and three sets. And we're basically going to go through a few different examples that follows all the rules we've seen before, and just see how they work here. One thing to note, we're not really going to get into an order of operations concept for this for these set operations. If we have more than one operation going on in a given set operation set thing, we'll put it in parentheses to make sure it's clear what should be done first, what should be done second. So let's start off seeing how we can shade a Venn diagram given the set notation for it. So, a few examples. First example, if I want to shade what the union of A and B intersected with C looks like, we'll have our universe. We will have three circles in here. And let me use the coloring like we had earlier. So we have set A, set B, and let's do let's do red for set C. Okay, so in here, first thing, parentheses say I should do the intersection of A and B first. So the intersection of A and B is this area here. I'll do that one in green. So this is both of these circles completely. If we intersect that with C, C being right here, we're looking to see where these overlap, and they overlap in this area right here. So where the green and the red both are. So let's get rid of all of that stuff and shade that area. That area is right here. Okay, another example, different sets. So if I have the intersection, sorry, the union of A and the intersection of B and C. So, same start, that'll be our universe. I'll have three circles, one for A, one for B, and one for C. And in here, first thing, the intersection of B and C is this area here that I'm marking in red. And the A, we know, is this whole circle right here. So if we're looking for where the union of A and the intersection of B and C, it's going to be anywhere that's shaded at all. So let's clear this mess off and shade everywhere that had any shading, which was the whole green circle, plus this portion right here where B and C intersect. So it looks like that. Now, we can go the other way as well. We can be given a diagram and write the set notation that goes along with it. So let's look at a few examples of that. And this time I'll just use the entirely same color for this. It's the way you'll see a problem in a quiz test or on the IB papers. So I'm not going to color code it with green, yellow, red, what have you. First example, the universe, 3 sets in there, A, B, and C. And let's consider this area right here. So in here, if you see this area right here is inside A, it's inside B, it's inside C, and nothing else is shaded, which means that this is going to be the intersection of A and B intersected with C. Now, as I said before, we're not going to get really very much into order of operations on set operations, but I could also write this as the intersection of A and the intersection of B and C. Or, since it's all intersections straight across, I could just write the intersection of A, B, and C. These all mean the same thing. We're not going to make a big deal out of that. Another example is this. So I'll draw my rectangle. Universe, 3 circles, A, B, C. And in this case, let's look at this one. So let me grab the purple color and shade in make sure I get all this shade in correctly. Okay, so this area, not in there. Let me do that a little bit better. But everywhere else in A and C. Okay, so in here we can see that everything that's in A and in C is shaded except for what's in B. Now, we can get everywhere that's shaded in A and B by doing the union of A and B. But I don't want anything, A and C, everywhere in A and C. But I don't want anything that is inside B, so I'm going to say that it also has to intersect what is not in B, or in the outside of B, the complement of B. So these are some nice examples with the Venn diagrams, 3 circles. You can do a lot of different things with this. We can also deal with finite sets like we've done before. So let me define a few finite sets. I'll just use very simple, I'll define them explicitly to begin with. So let's let the universe be the integers from 1 to 9. Let's let set A be those odd integers between 1 and 9 inclusive. Let's let B be one more than the multiples of 3. So that would be, we'll start at 1. Let me make that. And then go up by 3. 1, 4, 7. And let's let C be the primes. So 3 different sets. Interesting, not interesting, but 3 different sets. So we can do the same thing. We can look at this in terms of the more than using 3 sets with our set operations. So going forward, given the set notation, I would say the intersection of A and B and its union with C. Now, let's look at this a little bit carefully. So the intersection of A and B is what A and B share, which is 1 and 7, and nothing else. So this is the set containing 1 and 7. We know that C is right here, so I'll list that off. So union 2, 3, 5, 7. And the union just has everything that's in either one of these sets, which is 1, 2, 3, 5, and 7. So if you just work your way carefully through it, you can get these, even if there's more operations going on, you can get there. But it's worth noting, so with the Venn diagrams, we were able to nicely go forward and backwards with problems. With finite sets, it's not so cut and dry. So if I consider the set containing 7, and I try to go backwards to write it using this sort of set notation, well, it's true that 7 will be the intersection of B and C. But it's also true that it'll be the intersection of A, B, and C. And I could come up with some more, throw in some complements, do various things, and still make it come to 7. So if I'm just dealing with these finite sets, I don't have everything shaded in anything, I don't have a nice Venn diagram to look at, it's not it might not be clear, well defined, which one to write. So if you are asked this, this is correct, there may be a simplest case, there may not be a simplest case, there may be more than one that is similarly complex. But you can still do it, it's just a little bit more odd, a little more strange.